Okay, welcome again to Humke's study. Today I'd like to take a look at what we're going to do with these eigenvalues and eigenvectors. So as a first step, let me just look at a diagonal matrix. Let's make this 4, 0, 0, 3. So here is a diagonal matrix. What is this matrix geometrically? Well, if you look at it, if you look at the vector 1, 0, this maps the vector 1, 0 into 4, 0, which is 4 times 1, 0. And so this tells you that in this direction, in the one direction, this linear transformation will stretch the plane 4 times in the x direction. So this is like an accordion getting stretched out 4 times the width that it was before. Everything gets stretched out. In other words, if you take a square, that square will map into a rectangular band exactly 4 times the width that it started. That's what this 4 means here. This eigenvalue of 4 in this eigenvector direction means that things get stretched 4 times, and in this case, in this direction. And if you do the same thing with 0, 1, three is the eigenvalue in this direction. So this is an eigenvector of eigenvalue 3, and it tells you that things get stretched vertically 3 times. So if we take our same little square, this will map into that kind of shape, exactly 3 times as much. So this tells you what the whole matrix does. It does both those things. Stretches 4 times in this direction, 3 times in this direction, all stretching about the origin. So if we take a square centered at the origin, the image of that square will be 4 times as large in this direction and 3 times as tall. Unfortunately, it should have looked like a rectangle. I'll make it look a little more like a rectangle. All right, so the image of the yellow square will be this whole thing. Everything gets stretched 4 times in the x, 3 times in the y. These are easy to understand geometrically, but not only are they easy to understand geometrically, but they're very easy to deal with algebraically, doing the arithmetic. Now, suppose that this is not suppose that the basis we're dealing with is not the standard basis, but is a different basis, say some basis B1. Then if you take 1, 0 in the basis B1, it does not mean the x direction. Maybe 1, 0 is actually in B1. Maybe this is 2, 1. In the standard basis. So the basis B1, the first element of B1 is 2, 1. If this is true, then you are not stretching in the x direction, you are stretching in this direction. So there is the direction 2, 1. So the stretching that's going on means 4 times in standard direction 2, 1. So if you're speaking in the basis B1, this is what happens. This little extra interpretation that this doesn't mean the x direction, it means this direction. So you are stretching in this skew direction. And it would be the same thing if you had a different vector v2. No longer are you stretching the 0, 1 direction, no longer means the y direction, it means this direction. This is standard notation. Okay, so this is the advantage of a diagonal matrix, that it immediately tells you, if you know what the basis is, it immediately tells you the geometry. It also immediately tells you some nice things about arithmetic. We're going to deal with that next time. Now, let's take a particular problem and work through it a little bit in this regard. I'm going to have to look at what I want here. So 4 minus 1 minus 2. And the second row is minus 6, 3, 4. And the third row is 8 minus 2 minus 4. Now, this is the matrix that's on the sheet that I provided for this, so you can kind of go through what I'm doing. We got killed off. This is a nightmare. All right. Okay, I didn't quite get killed off. Maybe that's part of the video. If it is, this happens a lot. So now, anyway, this is part of the sheet that I gave you, and we're going to show that this matrix here has a diagonal form, and I want to try to analyze that diagonal form. But the first thing I want to do is find the eigenvalues and eigenvectors. You've had some experience, I think, on this homework doing it by hand, but I'm going to use Mathematica to do this. So I'm going to share a screen. Let's take a look at this. So here's my Mathematica file. And I already entered that matrix, so I'm going to enter it now. See, hopefully it did something. Yeah, it does something. So now I like to look at my matrices in matrix form. So that semicolon is going to suppress output for that. But I want to look at the matrix form of M. Okay, there we go. There we go. So there is the matrix that we want. And now I'd like to look for the eigenvalues and eigenvectors for this matrix. So let's do that down here. Eigensystem for M. There it is. So what does this tell you? That in this particular thing, this first part, the 2, 1, 0, these are your eigenvalues, 3 eigenvalues. So I'm going to write those on the board. I know you're watching my screen, but we'll look at this in a minute. Well, we've got 3 eigenvalues. Lambda equals 2, 1, and 0. Now, this second part actually tells you what the eigenvector basis is for each one. And I'll specify this. And we'll take a look at that. E lambda equals 2, E lambda equals 1, and E lambda equals 0. These will be eigenvectors, and that's what you've got in this second part. 1 minus 2, 2, that is the basis for the eigenspace where lambda is 2. And 1 minus 1, 2 is the basis for the eigenspace when lambda is 1, and so on. So we'll come back to this in a second, but I'm going to stop sharing and record this information. Okay, we're back. I hope. And so let's record this information. So we have bases for the three eigenspaces now. E sub lambda equal 1 will be equal to the span, all multiples of that very first vector. Now I've got to go look it up. The very first vector, 1 minus 2, 2. And E sub lambda equals 1 is the span of, I'm going to write this vertically, save myself a little space, of 1 minus 1, 2. And E sub lambda equals 0. Lambda equals 0 tells that those vectors get actually squashed. They get all sent to 0. So this has a projection. The determinant of this matrix would be 0 if we computed it. And so that would be 1 minus 2, 3. And that's the information that eigensystem gives you. It gives you this information here. It gives you a basis for each of the eigenspaces. So this mapping, this matrix represents a linear transformation from 3 space to 3 space, since it's 3-dimensional. And in this direction, it will expand by 2. In this direction, it expands by 1, so it leaves it alone. And this direction, it expands by 0, which means it collapses. So this is the information that we have. And now I'd like to look at the change of basis matrices. I'm going to erase a lot of this. And we want to look at the change of basis matrices here. Where we have 3 of these. These 3 vectors form a basis for 3-dimensional space. I'm going to call this B sub E the eigenvector basis. For 3-dimensional space found using M, the original matrix. So that eigenvector basis, I'm going to do it in this order. The order of the largest eigenvalue first is going to be 1 minus 2, 2. Second one is 1 minus 1, 2. And the third one is 1 minus 2, 3. So this is a basis for all of 3-dimensional space using these 3 eigenvectors. One eigenvector for each eigenvalue. So now, if we take 3-dimensional space with this eigenvector basis, B sub E, and transform from 3-dimensional space with the standard basis, the matrix that does that, P, is the matrix 1 minus 2, 2, 1 minus 1, 2, and 1 minus 2, 3. And the matrix that transforms you back will be P inverse. So this is the change of basis matrix between the eigenvector basis and the standard. Put the corresponding basis elements, these are eigenvectors, in the columns. And then P inverse is the inverse of that matrix. So let's go ahead. I want to go back to Mathematica and do this in Mathematica now. So we will try to share screen again if it works. There we go. So there's the eigensystem, and the eigenvectors are next to it. So let's take this last part. Those are the three eigenvectors written as rows. So I copied that. And now my next line, I'll let P equal that. Paste it in there. Return. Okay, we've got them in there. So now we'll use the matrix. I want to use matrix form to see it. Okay, and oh, wait a minute here. This put the eigenvectors in rows, and in order to be a change of basis matrix, they have to be in columns. So I've got P wrong here. P should be the transpose of what I have, making the rows columns and the columns rows. And transpose of that matrix. Let's hope I spelled transpose right. Okay, 1 minus 2, 2, 1 minus 1, 2, 1 minus 2, 3. This is what we want. This is the change of basis matrix. And now we can go ahead and find P inverse. I'm going to just call it P1. So this is the inverse. Okay, we're working, but I actually would like to see the matrix form of that. I want P1 to be the matrix, but I would like to look at the matrix form. All right, so there is P inverse. I'm going to record it on my board, and then we will, I'll come back. So the rows are 1 minus 1 minus 1, 2, 1, 0, and 2, 0, 1. All right, stop sharing. And we're back. So that form got us this information, that we have a change of basis matrix from the eigenvector basis to the standard given by P. These are the eigenvectors written in rows. And then we computed P inverse. We have 3 of these, so it is a basis for 3 space, but we're not quite done. There's a little bit more to the story here. I'm going to leave this picture here for a minute and kind of redo it. What we started out originally was R3 with the standard basis BS, and it maps into R3 with the standard basis. And our original matrix M is the one that does that. And of course, I've forgotten what M is right now, but I've got it written down here somewhere. 4 minus 1 minus 2. Minus 6, 3, 4. So this is the original matrix, 8 minus 2 minus 4. This is the original transformation. And now, if we draw this same picture, the exact same transformation with the eigenvector basis. So R3 with, I could have made these a little bigger. R3 with the eigenvector basis. This same transformation has a different form. The form is diagonal because it is an eigenvector basis. So the form will be diagonal. And what does this function do? Well, in the first eigenvector direction, it multiplies by 2. In the second eigenvector direction, it multiplies by 0. And then the third eigenvector direction, it collapses. Oops, this should have been the collapse. This should have been the 0. So this is a diagonal matrix. This is the same transformation, different name. But this name, in this form, it really tells you what it does. It doubles the first direction, leaves the second direction alone, and zeroes out the third direction. So as soon as you know what the eigenvector basis is, the columns of P, then you know this form. These are the same transformation, just according to different bases. Now, diagonalization has to do with these P and P inverse also. So I'm going to write it like this. We're going to look at this direction. What is the arrow in this direction? Well, here we are changing standard to the eigenvector basis. And so this is P inverse. Hope that green is showing up. Doesn't look the best. Over here, I'll use maybe orange. Over here, I want to go this direction, and I'll explain why in a second. This is called a blob diagram. And this is the matrix P. And we know what those matrices are. They're in this bottom, which I'm now going to erase to write an equation for you. But we know what those two matrices are. We already computed them. They're on the Mathematica page, and they should be on the sheet if you're following it. If we begin with M starts here and ends here. With a blob diagram, you can either get M by going straight across. So that would be the matrix that we had, 4 minus 1 minus 2, etc. Or you can go this longer route, first P inverse, and we're on the right because this is written as functions. So the first one you do is on the right. Then M prime, 2, 0, 0, 0, 1, 0, 0, 0, 0, and then finally P. So if you take the product of P inverse times this diagonal matrix times P, you get back to M. This is factored M into these three matrices. The outside ones are P and P inverse. The inside one is this diagonal matrix. And this is called the diagonalization process. This is the process of taking a matrix and diagonalizing it. Now you might say, well, what happens if M doesn't have 3 linearly independent eigenvectors? Then this process doesn't work. There are other processes, they're more complicated, but this process won't work. We're looking at matrices that do have 3 linearly independent eigenvectors. If you have 3 linearly independent eigenvectors, this process is good to go. And that's what this section is about, is to doing this process. The questions that I will ask are the questions that I've asked on this homework assignment. They include finding the linear transformation represented by this matrix, and then finding the diagonal matrix that's equivalent to it. And in this sense, finding the eigenvector basis for, or an eigenvector basis for the same space, R3, writing this equation, understanding that this equation is true, and writing this blob diagram. So I will ask you blob diagrams. So understand this diagram if you can. We'll talk about this tomorrow and start to do those problems. Thanks a lot. See you tomorrow. Have a good rest of the weekend.